for joining today's webinar. Just to go through a few housekeeping items before we get started, I want to remind everybody that you are on mute. So if you have any questions during the webinar, which we highly encourage that you ask, please submit those during via the question function on GoToMeeting. And the last part of the webinar, about 10 or 15 minutes, we'll go through as many questions as possible. Also, I just want to remind you that today's webinar is being recorded. So a recording along with slides will be posted to our website in about 10 days. I will be sending out an email once those post, but feel free to check back as well. And I also just want to remind you that this is a webinar series, so I encourage you to check back to our website as we do have these monthly, and we would love to have you attend some more in the future. So on that note, I'm going to introduce Dr. Nancy Garland. She is the Technical Development Manager in the U.S. Department of Energy's Office of Fuel Cell Technology. She leads the hydrogen and fuel cell manufacturing research and development activities and supports the fuel cell and market transformation teams managing research and development projects. So on that note, Nancy?
Okay, thanks, Allie. It's my great pleasure to introduce today's speakers. I'll just read a little bit about them. Dr. Nenad Markovic is a senior scientist and group leader at the Argonne National Laboratory. He's also Deputy Director at the Joint Center for Energy Science Research at Argonne. Prior to joining Argonne, he was a staff scientist and principal investigator at the Lawrence Berkeley National Lab from 1991 to 2005. He received his bachelor's, master's, and PhD degrees, all from the University of Belgrade. He was one of the pioneers in the application of UHV surface analytical tools and in situ surface-sensitive probes and spectroscopies to the study of electrochemical systems and the use of a surface science approach to the development of electrocatalysts for fuel cells and electrolyzers. More recently, he has advanced a surface science approach to the study of lithium surface chemistry and lithium electrolyte interfaces to advance lithium battery technology. He's the author or co-author on over 240 papers and 8 U.S. patents. He was the recipient of the Faraday Medal Award in 2013, the Distinguished Performance Award by University of Chicago Argonne LLC in 2012, and the U.S. Department of Energy R&D Award in our Hydrogen and Fuel Cells program in recognition of its outstanding achievement in reducing platinum group metal content for PEM fuel cells. He is also a fellow of the International Society of Electrochemistry. Our second speaker, Dr. Voja Stamenkovic, is staff scientist and tech leader at the Materials Science Division at Argonne National Laboratory. He received his PhD degree in physical chemistry from the University of Belgrade in 2001. He had joined Argonne National Laboratory in 2005 after spending 7 years at the Lawrence Berkeley National Lab. Dr. Stamenkovic received a recognition award from Lawrence Berkeley National Lab in 2004 and the Distinguished Performance Award from the University of Chicago and Argonne LLC last year. His research interests include electrochemical energy conversion and storage, design and synthesis of nano-mesoscale materials, spectroelectrochemistry, and bioactive materials. He's published over 100 articles and book chapters for which he's received over 5,500 citations. Gentlemen?
Thank you, Nancy. Thank you, Ellie, also for organizing this webinar. We are really very pleased to present our results, but let me first make a brief outline because both of us, Voja and myself, we are going to talk about our results. First, I make a very brief introduction about our approach. Then Voja would continue by introducing and showing some of our real results. At some point, I'm going to just briefly to mention that in addition to changing the electronic structure of materials, we are also working on modifying the catalyst by molecular patterning. Then Voja would continue with mesostructured materials, our very new and exciting results, and then Voja would close our presentation. Let me first start with the old way of doing electrocatalysis. This is something what was pioneered in early 60s last century. People would just characterize high surface area materials, focusing on shape, size, distribution, and bulk composition without paying really attention on surface composition and surface structure. Considering that electrocatalysis is basically a process which is taking place at surfaces, our approach is first to understand, certainly at atomic and molecular levels, the processes which are taking place at electrochemical interfaces containing both surfaces and double layer structures, and then how this correlation basically may affect bond breaking and bond making events in electrocatalysis. Now, our approach, this is something what we were developing the last more even than 20 years. We have basically two methodologies. One is what we call materials by design methodology, in which we start with single crystals, but always we are thinking about real nanoparticles. Usually we are designing materials, both metals, metal oxide and oxide. In addition to these materials by design, or if you like, electrode by design, we recently started also focusing on tailoring the double layer structure, because we are realizing that also the double layer structure within three angstroms or 5 angstroms is also contributing significantly to electrochemical processes. Boy is going to talk lots about the synthesis and characterization efforts. Just briefly, we basically base the best active sites or the most stable active sites. Now we are learning how to synthesize them. We have a variety of surface characterization methods, but the key is how to establish structure-function relationships, namely how to establish activity and stability mapping. And we have our own, I would say, unique way. We are always following the trends along periodic table. We learn from those trends, but the final goal is to apply all of the science on the left-hand side in real application systems. Again, this is at least we are going to show the flavor of our surface science approach. Let me start with, first of all, with bimetallic systems, simply because it has been realized that platinum itself cannot deliver at least high activity which is required in polymer electrolyte fuel cells. We start focusing on the platinum which are alloyed with 3D elements. Usually what I say, and I would like to repeat, platinum nickel is not something, the system that we discovered. UTC basically was working with platinum nickel in late 60s. However, they put all of these catalysts in the fuel cells even before understanding what is behind catalytic activity. So I am just going to demonstrate that one can use all crystals or all systems, but really to reach completely new electrocatalytic behavior. This is something what we got the data 10 years ago. This is some kind, as the title of the slide is saying, we are focusing on surface structure and composition. As I like to repeat once more, catalysis is something which is happening at surfaces. In this particular case, we were focusing on platinum-3 nickel. On the right-hand side, you can see the lead patterns of platinum-3 nickel single crystal surfaces. Each of one has unique arrangement of surface atoms. It's not that only arrangement is unique, but also using low energy ion scattering, we were able also to see what is on the surface. And as the results in the middle show, once the surface is annealed, on the surface is, due to the segregation, almost pure platinum, and there is very small contribution actually of nickel and cobalt. On the left-hand side are our new results. This is STM results, which are showing basically that in addition to UHV lead somehow investigation, we can also now see the surfaces, especially in electrochemical environment. Before these STM images, we were focusing a lot on X-ray diffraction scattering, and this is now the slide is just showing some of results, or this is combination of X-ray scattering and electrochemistry. First of all, what we can see on the top is unique, I would say, anomalous scattering results, which for the very first time established that in a electrochemical environment, platinum-nickel surfaces, in this particular case, platinum-3 nickel 111 surfaces, are segregated. I think this is, at least I'm considering this one of our biggest achievements, because now we know exactly what is on the surface. It's almost pure platinum. This is what we call the platinum skin. And this platinum skin, as we can see below, electrochemical result has unique electrochemical behavior. First of all, due to the unique this oscillatory concentration profile, which we are calling nanosegregated profile. There is also unique electronic properties of platinum surface atoms. This is the D-band center position, which is controlling absorption and catalytic processes. The key, at least with voltammetry, which is in the middle, is that due to the lowering of the D-band center, absorption of hydrogen and OH species is significantly reduced. This is in particular actually important for absorption of OH, because OH, which is formed in our case from water, not due to the dissociation of molecular oxygen, is absorbed on the surface, and this coverage by OH is controlling availability of platinum skin structure for dissociation of molecular oxygen. Based on this, we are also using Monte Carlo simulations, and this is also, I would say, our old results, where we were suggesting that somehow if one would be able to design or to synthesize octahedron nanostructures, then this structure may have unique catalytic activity and also stability, because at least molecular dynamic calculation shows that octahedrons are as stable as cubo-octahedron structures. Now, once we have defined the platinum skin structure, and in this particular case for platinum single crystals, it is actually very easy to establish, for example, how many active sites we have, because electrocatalysis, especially a specific activity, is based on the number of active sites, or if you like, the turnover frequency for the reaction. This is just one example which shows, for example, the upper part on the left-hand side is just absorption of hydrogen. Usually people in the fuel cells, they are using absorption of hydrogen as a measure for number of active sites. Certainly this is very convenient if, as in our case, we have single crystal surfaces, but Boya would basically demonstrate clearly that this is almost impossible to use in the case of high surface area materials. So we developed also another method, which is we were trying to establish the number of active sites based on CO stripping voltammetry, which is shown on the bottom of the left-hand side slide. And the key is for all of this is that, for example, in the case of platinum 111, if one would compare the charge required for formation of hydrogen UPD layer and stripping of CO, the charge is usually 1. However, in the case of platinum-3 nickel nanosegregated structure, the ratio between the charge for CO and hydrogen is 1.5. So the only way to know the number of active sites, or even to demonstrate that the platinum 3D elements have nanosegregated domains, is basically by following the ratio between the ratio between the charge required for formation of hydrogen and CO add layers. Now, based on this, I think it was, at least in our case, simply based on geometry of extended surfaces to establish catalytic activity. And as I said at the beginning, we are always focusing on the trends. We are trying basically based on trends to understand what is going on during the reaction. I'm not going to go in details, but only once more I'm just going to point it out that platinum-3 cobalt and platinum-3 nickel, they do have unique catalytic activity. We assign this to unique nanosegregated domains, which are also somehow confirmed with the DFT calculations. On the right-hand side, these are calculations which has been done by Jens Norskop. And again, in this, as in experiment, it was really confirmation that platinum-3 nickel and platinum-3 cobalt are sitting on the top of volcano curves. Now, if I go back to, again, to the left-hand side, one can see that we purposely put the activity of platinum-3 nickel 111, which is a couple of times more active than polycrystalline surfaces. All of these volcanoes are established for polycrystalline surfaces. This is something what we published 2007, and ever since we found the unique activity of platinum-3 111, our major target or our major goal was really to mimic or to try to find a way how to synthesize a nanosegregated structure of platinum-3 nickel 111. More about our approach and the details how exactly we are doing all of this. Now Voya will take over and to show some of our results.
Hi everyone. So I will continue with our effort in synthesis direction. So as Nenad indicated, the main goal was actually to see whether and how we can mimic those beneficial properties of platinum skin surfaces. And therefore, in order to avoid trial and error approach, which would assume synthesis of wide range materials without detailed insight into composition properties and particle size, we actually spent significant time to decide which method is going to be the method of choice for our effort. And pretty soon we came to the conclusion that colloidal solvent thermal approach is very powerful synthetic tool for tuning catalytic properties in direction that we would assume as desirable. So here is just one overview, actually, what kind of chemicals and procedures are involved in colloidal solvent thermal approach. And actually, the next slide shows one particular example, that would be platinum-3 cobalt nanoparticles, and those are results from high-resolution PEM studies and also effort to establish the exact elemental distribution. And one can see that different elements, platinum and cobalt, they are homogeneously distributed throughout the volume of one single particle. But what is even more important is very narrow particle size distribution, and this is a unique advantage of this procedure. So not only that bimetallic particles can be made, but lately we turned our attention into multimetallic systems and ability actually to synthesize ternary alloys. And here is a snapshot of 3 different alloys, platinum iron cobalt, platinum cobalt nickel, and platinum iron nickel. And you can see that in each case we were able to achieve homogeneous distribution of elements, and in addition to that, again, very narrow particle size distribution. So we are very focused on particle size as something which is very important physical property of the catalyst. And before we started the systematic approach towards nanoscale systems, something was lacking in the literature, and there is still, I would say, significant debate which is going on currently in society, whether particle size effect is real or not. For that reason, our first attempt in characterization and electrochemical screening was to see whether particle size effect applies for bimetallic systems. And here you can see that we used our colloidal solvent thermal approach to tackle this issue, and we were able to synthesize particles between 3 nanometers and 9 nanometers. And then we made systematic electrochemical characterization. And we were able to see that in terms of specific and mass activity, there is particle size effect, and sweet spot in terms of optimizing specific and mass activity would be somewhere around 5 nanometers. So from there, also, it would be important to recall some basics about what is the origin of particle size effect and why actually something which is supposed to be well established in the field is still subject of big debate. So here is a summary of literature data and our own data and our own explanation. And it's very obvious that small particles are very rich in edge and corner size, while with particle sizes, as one can see, those sites are diminishing, and therefore contribution of one-on-one facets is getting more pronounced. But fundamental explanation is coming from the fact that in catalysis, something which is definitely well established and nobody has doubts about that is the fact that structural composition is very important. So different single crystals of platinum, they have different specific activity, and therefore we believe that particle size effect is coming from contribution of different facets that are exposed to the surface. That would be a simplified and short explanation. So once we establish particle size effect, we proceed towards another challenging question, and that was whether we could do and whether we could mimic platinum skin type of behavior at nanoscale. So on single crystal surfaces, and as Nana mentioned, platinum skin was achieved by annealing. And also it is well known if we anneal nanoscale catalyst, then we can basically sacrifice that nice and unique particle size distribution, because substantial amount of particles are going to agglomerate, and therefore instead of looking into average particle size of 5, then we would end up with something which is shown here on insert D, where substantial agglomeration took place. So we spent significant time in exploring whether we can optimize annealing temperature to the level where agglomeration is not going to be obvious, and that's a temperature between 400 and 500 C. At the same time, we were following how annealing would affect electrochemical properties, and therefore we could see that starting from 300 C and going to 400 and 500, we could see substantial increase in specific activity, and that was a clear sign that beneficial and desirable surface composition and near surface composition was taking place at nanoscale too. And therefore, again, we were able to determine what would be the sweet spot in terms of temperature treatment, which would allow us to achieve that platinum skin beneficial behavior and plus to avoid agglomeration. So, so far we were focused on platinum 3 nickel or platinum 3 cobalt, and in more general terms, I would say platinum 3M. Systems where M stands for any kind of metal that we use. And certainly our goal was not only to explore platinum 3 or 3x1 systems, but the final goal would be to minimize the amount of platinum in the system in order to make catalysts more affordable and less costly. So here we increased the platinum-nickel ratio going from 3x1 all the way to 1x3, and certainly a crucial question was what would happen with nickel which is exposed to acidic electrolyte. And we performed careful study that involved not only electrochemical characterization but also characterization by high resolution PEM, and we were looking and we were focused in composition change before and after exposure to electrochemical environment. And therefore here you can see the summary, actually what would be average or what would be bulk composition in case of different catalysts. And I will pick the one which is here labeled with red color, which is platinum nickel, with, and platinum nickel after leaching becomes bulk ratio or average ratio between platinum and nickel becomes 3x1. But also everybody should remember that finding applies only to the entire amount of catalyst, and therefore it is still questionable actually what and how surface composition looks like. And this is a cartoon which explains that actually everything which was exposed to electrolyte is dissolved. There is no nickel on the surface. However, nickel which is inside of particle is still protected, and the amount of nickel in particles still stays in the amount of 50%. So from there, actually, we wanted to see and tackle to more in more controlled way, actually, how we can further manipulate those surface properties. And therefore, we went back to our expanded surfaces, and here we relied on thin film approach. So not only that we were able to vary and control bulk composition, so we were also able to simulate different thickness of remaining platinum on the surface that we termed platinum skeleton. And here we varied the thickness of platinum skeleton from 1 all the way to 7 monolayers. So, and one can see that once we started to deposit several monolayers, going from 1 to 3 all the way to 7, actually specific activity started to drop. And specific activity of surface, which had 7 monolayers of platinum, was very much the same as polycrystalline platinum. So again, we were able to establish sweet spot in terms of the thickness of remaining platinum skeleton, and that was found to be 3. So 3 layers of platinum skeleton is thick enough to preserve further dissolution of nickel, but also it is, again, thin enough still to provide that beneficial effect of subsurface nickel. So from that point, the main challenge was whether annealing of platinum skeleton, which is as thick as 3 monolayers, would bring and resemble properties of ideal platinum skin 111. So we gently annealed that again at the temperature which was somewhere around 400 and 500 C, and we could see that properties were substantially changed, and specific activity was increased by a factor of 8 compared to polycrystalline platinum. And that was clear indication that we were able to achieve platinum skin type of behavior. So from that point, we accumulated, we took and transferred that knowledge to nanoscale systems, and basically we applied the same protocol. So we used as prepared platinum nickel particles, then we exposed to electrochemical environment in order to get platinum skeleton and to get rid of unstable nickel, surface unstable nickel, and then we annealed. So the final result was particle that has up to 2 layers of platinum. And those 2 layers turned out to be extremely beneficial. So not only that hydrogen UPD region was changed in terms of comparing to corresponding platinum-carbon catalysts with the same loading, but also we could see exactly the same behavior as Nenad mentioned from the single crystals, where unique adsorption properties appeared in terms of substantial difference between hydrogen UPD and CO stripping charge. And therefore, that was another confirmation that we were indeed able to produce platinum skin nanoparticles with multi-layered platinum skin. So here is the slide which explains summary of electrochemical results on this catalyst. And one can see that not only activity was substantially higher. On right-hand side, you can see values that are obtained at 0.95 volts. And we decided actually to shift our potential where we are comparing and observing activities in our RD experiments, because 0.9 volts would be too close to diffusion limiting region. So 9.5 would be more accurate in terms of getting the exact insight into catalytic properties and specific activity. And therefore, multi-layered platinum nanoparticles with nickel inside, they showed activity which was initially 6 times, almost 7 times higher than platinum catalyst. of the same size and the same loading. But what is even more impressive is how that catalyst behaved after 20,000 cycles between 0.6 and 1.1 volts. And one can see that specific activity drop was really negligible. And the main reason for that is the fact that specific surface area did not change. In other words, we were looking into catalyst which was at the same time very active and very stable. So, and total surface area loss was somewhere around 10%. And if one compared that to state-of-the-art platinum carbon catalyst, that goes up to 40%. So the final properties are 8-fold increase in specific activity and almost 10-fold increase in mass activity over platinum carbon catalyst. So not only that we can tackle issue of stability with bimetallic systems, but also our goal was to explore what is going on with multimetallics. And here is a typical example actually how pure platinum catalyst looks like before and after 60,000 cycles. So morphology is substantially changed. And for that reason, we introduced concept of multimetallic particles, and our goal was to see whether additional elements such as gold can change and how the mechanism of improvement is going to work and is going to affect catalytic and durability properties. So in this particular case, we used gold seeds, and then we covered gold seeds with bimetallic shell, in this particular case platinum iron. And also we wanted to compare how all of that is going to fit with and how it's going to match activity and durability of comparable pure platinum iron particles, which is given here. So the same particle size and the same loading. We did a number of characterizations, including high-resolution PEM and also elemental mapping, and it was confirmed that gold stayed inside while platinum shell and with iron was around the particle. So here is the summary of what was obtained after careful electrochemical studies. So first two lines, they show how platinum and how platinum bimetallic particles would behave after extensive cycling. So there's a huge change in morphology, and also all of that affects loss in surface area and loss in specific activity. However, for those ternary alloys, we couldn't see any change in morphology, and the final outcome was the fact that mass activity was more than 10 times higher because there was no loss in surface area. And also we were able to gain substantially in specific activity. But what is intriguing is explanation of the mechanism of improvement. So, and in order to explain that, we used again our Singer crystals that were initially covered with pure platinum, with bimetallic film, and also we used gold to compare. And one can see in the background that cycle photometry of gold and bimetallic systems is substantially different. And the onset of oxide formation on platinum and platinum bimetallic starts as low as at 0.6 volts, while at gold it starts at potentials that are higher than 1.2 volts. So, in other words, there is a substantial difference in oxophilicity, or actually affinity to absorb oxygenated species, and that is coming from the fact of different fundamental properties of gold and platinum. One can even say that gold is more noble because it's more resistive to it's more difficult to oxidize. And in this particular case, gold, which sits inside of particle, stays over there. But huge difference in surface energy between gold and platinum provides tendency of gold atoms to constantly be to constantly approach a surface of the particle. However, in an electrochemical environment, that never happens because platinum surface is somehow stabilized by those surface oxides. In case that gold is not present, we wouldn't have so-called counterbalance effect, which is coming from the two opposing forces. One is from the subsurface gold, which has tendency to be on the surface, and the other one from surface oxides that are trying to pull platinum out, and in other words, to dissolve platinum. So that was our explanation of how we were able to stabilize. So here I would switch back to Nenad, and he's going to mention how, in addition to nanoscale catalysts, we were able to introduce catalysts with self-assembled layers.
The next three slides, and I'm going to go very quickly because we are short with the time. The next three slides are provided for two reasons. One reason is to demonstrate that somehow electrocatalysis is more than just changing the electronic properties, which we have discussed so far. The second one is because the results which I'm going to show are what we obtain are provided, and basically the support what we got is coming not from ERE program, but is coming from a DES program. We purposely put these three slides just to demonstrate how important the synergy between DES and ERE is, and how it basically should be even more enhanced in the future. The results, what you can see right now, is just something that we try to, as I said, to keep the electronic properties of material, but to change catalytic activity by molecular patterning. In particular, this is the case for very slow reaction rate or kinetics of oxygen reduction in phosphoric acid fuel cells because of absorption of phosphoric acid anions. Now the voltammetry is basically on, and in this particular case, what we try somehow to protect absorption of these anions, which are blocking the availability of platinum sulfide by cyanide. This is a method what Itaya introduced in the 1990s. And in this particular case, what you can see right now, we managed somehow to make very nice structure of cyanide on platinum 111, and this cyanide distribution of the surface is such that allow small oxygen to go through, but somehow not to allow a big phosphoric acid or sulfuric acid anions to penetrate and to be absorbed on the surface. This is almost like a shielding way how one can make high selectivity to be selective only for the oxygen reduction reaction. And if for this system somehow we manage to go from very inactive platinum 111 in sulfuric acid solution, which is the black curve, to the red one, which is activity on the surface, which is covered with cyanide, the activity is almost identical as in the case of perchloric acid. The second example is more about stability. It is very well known that due to the start-stop conditions and due to the undesirable oxygen reduction reaction on the anode side, there are problems with the potential at the cathode side, go to very positive potential, and then the electrode is becoming very unstable. We managed somehow, our goal was somehow to modify platinum surfaces in such way that, again, it would be selective, but in this particular case just for hydrogen and to reject oxygen. Certainly, this is much more actually a tough thing to do, simply because oxygen is also rather small. Nevertheless, on the surface, which you can see, this is for platinum 111, if surface is covered with 98% of these calixaren molecules, then the hydrogen oxidation reaction is almost identical as on pure platinum electrode, just demonstrating clearly that turnover rate of the hydrogen oxidation reaction is very high. In contrast to hydrogen oxidation reaction, oxygen reduction reaction is completely ceased. So this type of materials can be nicely used as the anode material, which would somehow allow hydrogen oxidation reaction to take place under the full rate and almost completely to suppress the oxygen reduction reaction. The very important thing is that all of this knowledge from single crystals we manage to completely transform on nanoparticles, and this is something I think what is really important for making selective nanomaterials. This is just, as I said, just to give you a flavor about our transformational methods, starting from single crystals and ending up with high surface area catalysts. I think the next couple of slides, Boya is just going to demonstrate that this is not only the case for the oxygen reduction reaction, hydrogen oxidation reaction, but also on the mesostructured platinum nickel catalyst. So Boya would continue with our recent results.
So far we were focused on single crystals and corresponding nanoscale materials, but also all the time we were actually aware of substantial difference in terms of performance, especially in terms of huge difference in specific activity. So we wanted to explore in more details actually what is going on with another class of catalysts, so-called thin film-based materials that are initially introduced to fuel cell community by 3M. So, we were aware that thin film methodology provides huge potential actually in tuning catalytic properties and also ability to tune composition. And what was lacking was insight into ability how and whether structure can be tuned as well. So we went to extended surfaces of thin films, and one can see morphology of as deposited pure platinum thin film over glassy carbon substrate. So there was no any single crystal as a support or single crystallinity in the beginning, and voltammetry actually resembles voltammetry of what is supposed to be polycrystalline platinum, which is given here as a solid white curve. But after careful annealing, actually we could see appearance of single crystalline facets, and more importantly, the entire surface actually gave us feedback which was more or less single crystalline type of surface, which nicely distinguished butterfly region, which is fingerprint property of platinum 111 surface in perchloric acid. So we were amazed by that after careful treatment, we could indeed not only tune composition eventually, but also structure as well. And our next step was to explore how all of that would work on corresponding platinum, nickel, or bimetallic systems. And here one can see voltammetry of as deposited versus annealed. But what is more important was to check catalytic properties. And initially, polycrystalline film after annealing became indeed 111-like, which is confirmed by extremely high catalytic activity, which was as high as 75% of the most active platinum-3 nickel 111 skin surface. And that inspired us to go back and to see how all of that can be applied to practical catalysts. In this particular case, we were looking and working with 3M type of catalyst, and one can see initial surface morphology is highly corrugated with nicely pronounced features on the surface and highly grained structure. So we applied our annealing protocol, and we were following in situ TEM in order to see and follow how surface and near surface morphology is going to change. So that would be initial stage, and then after several minutes we could see the surface was getting smoother, and finally we ended up with surface which was clearly rich in crystalline facets and almost completely flat. So what was intriguing again was to check electrochemical properties, and regardless of slight loss in specific surface area, because we were going from highly corrugated to more smooth, we were able to observe substantial increase in specific activity. So what is important here is to provide the final overview slide in whatever is available now in terms of different classes of catalysts. And one can see region of platinum nanoparticles that sit below the region of activity of polycrystalline materials and polycrystalline alloys, which can be up to 4 times higher than polycrystalline bulk platinum. and also target activity is given here, which is almost 20 times more higher than corresponding polycrystalline platinum. So in case of so-called mesostructured thin films that we just presented, we were able to achieve and approach that region which was previously reserved only for single crystals. And this is I would say, substantial new finding, and also it provides completely new approach, and hopefully in future we are going to have more chances to work with those systems in terms of applying different substrates, and certainly ability to control composition and compositional profile together with structure is going to open completely new direction in catalyst design. So here is the last slide for today, which is summary of whatever was achieved, and the message to take home would be that our approach and knowledge from single crystals and well-defined systems is really essential, actually, and we are using that as a guideline to control and to perform systematic approach in corresponding practical catalysts. So I purposely said practical catalysts because they can be at nanoscale or mesoscale. They can be nanoparticles or mesostructured thin films. And so far, in practical catalysts, we were able to achieve enhancement in activity, which is as high as 20-fold improvement for the oxygen reduction reaction. And from here, I would like to mention and show our collaborators, and certainly acknowledgement to funding agencies, and for whatever we presented today, we received funding and support from DOE Office of Basic Energy Sciences and from DOE Office of Energy Efficiency and Renewable Energy. Thank you very much for your attention, and we will be happy to take your questions.
Well, thank you, Dr. Markovic and Stamenkovic. It's truly outstanding, amazing work. We have one question. We'll start off with, you mentioned ways to reduce the oxygen reduction reaction on the anode, and the question is, one of the causes of catalyst layer degradation is corrosion of catalyst supporting carbon during start-stop cycles at high cathode potentials. Are the new platinum M catalysts more stable to carbon corrosion at potentials greater than 1.1 volts? Yeah. Do you have any data?
In our case, for example, right now, we are really focusing a lot on stability. And this is no doubt that this is going to be the key for the development of fuel cell technology. Regarding the potential window of stability, if you like, in the case of platinum, let's say bimetallics, what we know that there is a kind of what we call the gray zone, and these catalysts are stable between, I would say, 1.1 volts. If one would go above 1.1 volts, definitely then the corrosion of both platinum and especially non-noble 3D elements would happen. Now, this is everything, again, what we have right now is on very well-defined systems. Considering corrosion or considering carbon, I would expect certainly, especially in the fuel cells during the start-stop conditions, that also corrosion of carbon would be substantial. We should keep in mind that platinum is also acting as an catalyst. But considering that somehow we can really completely block with very simple method, that we can completely block the oxygen reduction on the anode side, what we are expecting, that somehow the cathode would stay really below or around 1.05, 1.1 volts. At this potential, I think most likely we are going to have a stable material and hopefully also to have stable carbon.
Okay, thank you. The next question is, how are these catalysts performing in real fuel cell environments with respect to activity and stability?
So we performed several MEA studies on our catalyst of choice, which is multi-layered platinum nickel, and we were able to repeat the exact same performance in terms of specific area loss, which was somewhere around 10% only. However, specific activity was not as high as in case of our RDE measurements. And it is important to emphasize that those measurements were not optimized, and we actually had to rely only on small amounts of catalyst, considering our limitation in our own lab, actually, and fact that we cannot produce huge amounts of catalyst. And those findings from MEA we were extremely encouraging, and therefore we are going and we have to continue in further characterization in MEA. But definitely it is important to be focused on optimization and on the exact loading that one is using in MEA, because also the amount of and interaction between ionomer and our catalyst is also something that we are focused on. So when combined all together, I would say at this point extremely high durability is confirmed, and certainly substantially increased specific and mass activities are also confirmed in fuel cells as well.
Great. Can you address the cost and the manufacturability of your catalyst?
So currently we are working in that direction, and we don't see, from fundamental standpoint, we don't see any limitation. However, once we approach stage where we can, in scaling up, which is going to be our next step, we can say more. But at this point, whatever we tried actually worked very well, and we were able to increase only by few factors our amount of catalyst for a single batch in our lab. But considering that pretty new, we are going to rely on our new labs here at Argonne, we do expect that our capabilities are going to be substantially increased in direction of scaling up.
Great. And last question is, are automobile companies and actually in other industrial sectors, are they looking to use your catalyst given the outstanding results?
We've been approached by several companies, and also we had several contractors also from that side. And in the meantime, also we licensed. We have several patents on platinum skin type of catalysts. So definitely there is interest, and hopefully in near future we are going to see more and more. And I would say the bottleneck now is actually to approach that scale-up capabilities from our end in order to provide substantial amounts of catalyst to be tested in MEAs.
Right. We're looking very forward to that. I think that's it for the questions right now, so I'll turn it back to Allie.
Thanks, everyone. What a great presentation, and thanks so much for the questions, you guys. Just some few quick reminders. This webinar was recorded, so we'll be posting that to our website along with presentation slides. In about 10 days, I will send an email out to everybody once that is done. And just a reminder, this is a series, so I encourage you to check back to our website for future webinars. And thank you so much, Nancy. Thank you, Voya. Thank you, Ninad. It was a great presentation, and look forward to the next one. Thanks, everyone.
Thank you, Allie and Nancy, for organizing this.
Appreciate it.
All right.